Hello and welcome back to another LeetCode problem. We're looking at LeetCode 215, a medium problem, and it's about finding the kth largest element in an array. So we're given an integer array nums and an integer k, and we should return the kth largest element in the array. Note that the kth largest element in the sorted order, not the kth distinct element. All right. Can you solve it without sorting? Constraints. Okay, we have positive and negative numbers, and we have at least one element in our array, and we know that k is actually also an index in the array. So that's nice to know. For our runtime and space complexity analysis, we're going to generously ignore the fact that this actually has an upper bound. Otherwise, everything would automatically constant space and constant time, which is no good. So yeah, so let's have a look at this example. So k is 2. We want to know the second largest element. So we have a 3, we have a 2. Right now the second largest element is 2. Now we have the 1. Well, 1 is smaller than both of them, so we're going to ignore the 1. Now we run into 5. Okay, that probably means we have to remove the 2. And now we have 3 and 5. In our mind. Then we encounter the 6, so that means we need to forget the 3. And we have 5 and 6 when we encounter the 4, which is smaller than them, so we ignore them. So the second largest one is then the 5. Cool. Now for the case of 4, we're going to, it seems like obvious that we need to remember what were the 4 elements, the 4 largest element we've seen so far. Right? And then draw out the smallest one when we find something that is larger, I guess. Well, we have to add the new element, somehow sort that thing, and then remove the smallest one. So then we run into the 2, so we will have 3, 3, 2, 2 in it. Then we run into the 4, so we pop out a 2 and have 2 3s. Then we pop out the other 2, now we have 3, 3, 4, 5. Then we pop out a 3, and then we have 5, 5, 4, 3. And then we pop out the last 3, and now we have 6, 5, 5, 4. And 4 is the smallest one, so the fourth largest one. Alrighty, so yeah, well, the simplest approach would be actually with sorting. So let's just do this for fun. So that would be O of n log n time, because we know n log n time. And since sorting is in place and it's O of 1 space, we don't need any extra space. So we do nums.sort and reverse is true. I can never remember if it's reversed or reverse. Well, we'll find out when I run into a compilation error or the execution error here in a second. And then we return nums at position k minus 1, because k is not 0 based, it's 1 based. So yeah, let's run this, see if that works. Reverse, yeah. So reverse is correct. So this will work. And if I submit this, happy times. Okay, so, but can we solve without sorting? Yes, we can. So we could approach like a kind of a sliding window approach, but we only keep the k largest elements in our sliding window. Similar to what I just did when I went through the example by hand. So we could do that. And then we could reduce it to maybe, well, let's see. Well, we will need at least k space. That's what we know. But let's see how we can reduce our runtime. It kind of depends on what we do. So what we could do is we could iterate through the array. So that's O of n times. And now we do k log k if we always sorted the window. Let's do that approach. And that would be for I in range, then nums. We'll have our little window. Window equals, there's nothing in the window. Window.append nums at position I if length of the window is larger than k. That means we have too many elements in there. So we're going to sort our window, reverse true in reverse order, and we're going to remove the smallest one, window.pop. That's what we will do, pop, right? So that would be n times k log k time. And then finally at the end, well, we will sort it for one more time because we don't know if we actually ran into that. Maybe if k is exactly the length of the array, this will never catch and we will never have sorted anything. So we will just do this. And the kth largest element is the smallest one in our k window. Let's see if that works. And that works as well. So let's submit that. Oh no, what's going on? Why is this taking so long? Time limit exceeded. Okay, so, and with k being insanely large. So this is, what is 2 to the 16 or something? So yeah, that is, oh, there you go. I did this month before. But yeah, so, but I didn't do all the variations. So this approach works, but we're screwed if k is large. So now there's another solution that we can take, and that is we don't have to sort the entire window every time. But what we could do is we could use a heap. So inserting and removing elements from a heap would be only log of k time when the heap is size k max, right? So we will do that. So we'll use a little heap, and we'll use a heap push and heap pop, which we have to import from heap q import heap push heap pop. And then what we just do is we do heap push into the heap. We're going to put element nums at position I, right? Now, since a heap in Python is always a min heap, there's no max heap, we need to do a little bit of trickery because we want to have the maximum elements in the heap. So we're going to put the negative numbers in there, right? So that means the small, if we have a large number, let's say 10, it'll be minus 10. And since it's a min heap, the minus 10 would maybe be on the top of the heap. And if we insert a 2, which would be inserted as a minus 2, that's not going to be top of the heap. It's because 2 is smaller then. Anyway, so that's what we do. And well, if we overflow, then we just pop out the element. That's it. And in the end, we just pop the last one. And yeah, that should be it pretty much. So heap size is maximum is k. And every time we insert or remove something from a heap, it's a log k operation. And since we have n elements in our nums, we are going to run push and pop at most n times. So that's our space complexity, our runtime analysis. Wrong answer. Oh, because when we pop element out, we have to reverse the minus sign, of course, since we are dealing with a max heap. KK5. Okay, that's not good. What's happening here? Let's see. Am I thinking wrong? Was max heap the wrong idea? I should have stepped through an example before trying to run this. Okay, let's say k is 2. We put in 3. So since we are dealing with a min heap, put in minus 3 into our heap. Then we put minus 2 into our heap. In the min heap, the smallest element is at position 0, so at the top. Next, we're putting in minus 1 into the heap. And because we're overflowing, we're popping. But because we made the mistake of making this a max heap. We're popping actually the largest element out. Okay, so that is, I guess, a brain fart on my part. Make this a max heap instead of a min heap. Yeah. So we have to use a min heap. Yes, we have to make it a min heap. That's a common mistake that I make. Hopefully you don't make that one. Mix it up between min heap and max heap. Yeah, but that is the optimal solution. And yeah, play around with this. Maybe explore min heap and max heap in Python. This heap queue is one of the few data structures that you actually need quite often when solving LeetCode style problems. So that is a good one to know. Yeah, happy coding.